Okay. Hello, everybody. It is our great pleasure today to host Dr. Prasanna Balaprakash, who comes from Argonne National Laboratory, where he's a computer scientist at both the Mathematics and Computer Science Division and also at the Leadership Computing Facility. Prior to working at Argonne, Dr. Balaprakash was the Chief Technical Officer at a startup, machine learning startup company in Brussels. And before that, he got his PhD at the Université Libre de Brussels. He is the recipient of several very prestigious awards, including the Department of Energy's Early Career Award. And today he'll be talking to us about scientific domain-informed machine learning.
Hey, thank you, Professor Papo. Thanks for hosting me today. And thanks, Jasmine, for all your help with organizing this talk. I really appreciate. And yeah, so today I'm going to talk about artificial intelligence and machine learning in Department of Energy, and specifically what we are doing on in that space at Argonne National Lab. Before actually talking about the machine learning aspects, I would like to first start with a generic introduction to the national labs. So first and foremost, why to pursue science in national interest? Because we do science in the interest of nation, and the Department of Energy is all about that. And there are several reasons for that. So, the questions that we were typically asked are, are you curious about unlocking the mysteries of the universe and try to figure out how the stars are formed or how the galaxies evolve over time, and trying to understand what was the beginning and what was the end, what is going to be the end, right? So, and are you enjoying working with others as a team to solve really, really hard problems such as climate change or fusion science, which is the grand challenge for energy. If we crack that problem, all our energy problem is going to somehow disappear. Or want to make lasting contributions to humanity, for example, discovering new drug for cancer, or recently, if you have seen the news from the Department of Energy, we have developed several methodologies for COVID related problems, starting from drug discovery all the way up to infrastructure analysis and so on and so forth. And finally, it's like you want to contribute to this to secure the nation's infrastructure, such as power grid or water and the related infrastructure that is the backbone of the entire country. In a sense, it's if you ask the question like do you want to wake up every morning and say, I want to solve a problem that no one has ever solved, and you want to go and solve the problem, and that's the sort of problems that we look at. All these problems are with the rest related to the national interest. Department of Energy is effectively, we call it's a department of science. It's not specific to energy, and recently we call this as a department of everything. Department of National Labs are sort of, DOE National Labs are the largest scientific research systems in the world. And I would like to sort of point out that, if you look at STEM spending, STEM investment from the government, so DOE is right at the top, and with a significant portion, if you are into math and computer science and other STEM areas, it's a significant portion of investments, millions of dollars, and it's much bigger than other entities such as Department of Defense or NSF or even NASA. The national labs grew out of Second World War. Primarily, they were involved in the development of atomic bombs, and that's where the history sort of goes back. And in particular, Argonne, is a sort of born out of Fermi and splitting the atoms at the University of Chicago. That's sort of formed the basis of sort of birth place or birth experiment for Argonne. DOE labs often work on big science, multidisciplinary teams. It's not a single person endeavor, but it's a think of hundreds of people working on mission-driven problems and trying to find solution to the problems. And these are really, really complex R&D challenges. It's not something that we can do it as a single person or a small team, but we collaborate with multiple people across the lab, across the universities. We have a lot of collaborators from the universities, with the grad students and so on and so forth. So it's and also with the industry as well. So it's a highly collaborative environment where we all come together to solve complex problems. And again, it's not the mission science. So yes, we do mission relevant problems. We do mission relevant science, but some of these research are also basic, fundamental. For example, if you are involved in material science, if you want to find a new material, it's not something that we can do that in a very applied way. We have to go all the way back to molecular science and try to understand what the molecules are and how we can sort of tinker with that molecular structure. So this is all basic science. And then how to take that and convert that into applied science and make something out of it. So it's a wide spectrum of research that we are doing. There are many important discoveries that came out of national labs. I'm particularly coming from the supercomputing and machine learning background, and there are several advancements in the area of supercomputing where we develop new type of algorithms, new applications that take advantage of really massive scale supercomputing capabilities and solve problems that cannot be solved otherwise. And why it is necessary to do those type of innovations is that whatever innovation we do, both in the hardware and in the software and in the application, eventually become a sort of a basis for your cell phones and computers 20 years after. So whatever you see now in your computer and in your cell phones, these were sort of innovations that happened 20 years back in the supercomputing area. So that eventually fed into revolutions in laptops and your cell phones. There are many other examples, starting from optical digital recording all the way up to safety and security, and also there are 16 elements and quarks that were discovered at the national labs. And national labs also it's also a very innovative environment, which has led to several scientists winning Nobel Prizes. Okay. So national lab, as I said, national lab system is composed of several labs, and we call this as multi-purpose labs, National Nuclear Security Administration labs, and so on and so forth. So the multi-purpose labs are the one that you can see here: Argonne, Brookhaven, Lawrence Berkeley, Los Alamos. So these are the multi-purpose labs where you say, the one in blue color, Fermi, Argonne, Pacific National Northwest, and Lawrence Berkeley, and so on and so forth. And the National Nuclear Security Administration labs are the Lawrence Livermore, Sandia National Labs, and Los Alamos. So they do more, they do research which are sort of related to nuclear security administration. By definition, it is not as open as the multi-purpose labs, but they do really cutting edge research related to the nuclear security administration. And then there are other labs, which is we call as single purpose labs. And they have a single mission. They don't have like multiple programs, but they have single mission to serve. So this is another view of national labs. So you can see the multipurpose labs at the arc, the blue here. These are all the multipurpose labs where anyone can work, and they have multiple programs starting from computer science all the way up to material science and cosmology and so on and so forth. On the other hand, these labs like Fermi, Jefferson, and Princeton Plasma Physics Lab, these are mission-driven single program labs, which is basically the Princeton Plasma Physics Lab primarily focuses on fusion energy sciences. They do they don't do anything else. Their single core mission is to work on this fusion energy sciences challenge problems, and how to build and control fusion energy reactors so that we can extract a lot more clean energy than what we can do now. And similarly, the other labs. So each of these labs have different purposes and different mission, and they work on this single program based on that. Okay, so with that, I would like to jump into the scientific domain-informed machine learning subject, and I would like to sort of pause here and see if there are any questions about national labs in general, or what we do. Okay, so okay, then allow me to go into the subject. Okay, so my talk is on machine learning, and in particular, as you all know, machine learning and artificial intelligence, they are all sort of used in an interchangeable way. And often, when I start a talk, I want to give a definition. And if you have to define artificial intelligence, it's a very difficult term to define because intelligence in itself is very hard to define. What do you call as an intelligence, right? So for the sake of this talk, let's call this as an automation of intelligence. And I put an asterisk mark on the intelligence because intelligence is somehow loosely defined. Okay, so it's about automating some actions that we do in a normal way, but now we can use computers to automate that. So that's a sort of mechanistic way of looking at things, but that serves the purpose, at least for this talk. I'm not going to go philosophical in this way. Okay, so artificial intelligence, broadly speaking, it's a very large field, and it's a high-level algorithms, concepts, and methods that we use to build intelligent systems. Machine learning is a promising approach to build such intelligent systems. So it's a data-centric approach. What does it mean? It uses a lot of data. It consumes a lot of data to extract or to learn something from the data and use that learning capability to perform actions in an intelligent way. And if you have to go back and see, okay, so why all of a sudden you see artificial intelligence and machine learning a lot more in the press as opposed to, let's say, 10 years back, is for this one particular method called artificial neural networks, which is a subclass of machine learning. It's a one particular approach of machine learning, which is sort of loosely inspired by how the neural networks in our brain works, loosely again. But that has led to a revolution in several fields, and that eventually changed the way that we do science at the national labs as well. Okay, so before entering into the nitty-gritty details, I want to sort of say why we are pretty excited about machine learning in particular at the national labs. Okay, so let me start with the simple problem. Take the problem of adding two numbers, right? So here is a problem of adding two numbers, and what we usually do as a computer, as a programmer, what we look at. Okay, so here is a problem. I have to take two numbers and I have to add that number. Okay, great. So what we do is to come up with a set of steps to solve this problem. And we say, okay, we start, take two numbers, add those two numbers, and then print the sum and end. So this is a set of logical steps that you can follow to solve this problem. And then once we figure out those steps, then we convert that into a computer program. And then once we have that computer program, right, we can give that computer program, we can load the computer program in the computer and then give inputs. And then we can get the outputs, right? So you give the program, you give the input, and you get the output, right? So the manual process, or it's on the humans to sort of figure out the sequence of steps and to translate those sequence of steps into a computer program, right? And as we all know, as soon as a human is involved in a process, it becomes a bottleneck because we cannot scale them, right? For a simple problem, everyone can do it. imagine if it's a very complex problem, dealing with modeling, weather phenomena, right? So it requires a lot of domain knowledge. Someone has to come and sort of, come and figure out what are the sequence of steps to model them, and then translate that into a computer program with thousands of lines of code, and then run that on a big supercomputer to do weather model, right? So that's a difficult process, time-consuming process. And often it's sort of limited by the human knowledge. Okay, so machine learning, on the other hand, sort of changes this entirely. Okay, so machine learning, one way to look at it is gives the computers the ability to learn without being explicitly programmed. Okay, what does it mean? So take for this example, so same adding two numbers. Now what we are going to do is take a lot of input-output examples, which means that, okay, I'm going to generate input like 1, 1 and output 2, and another two numbers and their corresponding output, and so on and so forth. I'm going to generate thousands of such examples. And then I'm going to give input, give them to a machine learning system. And this machine learning system will figure out a program from the data, from the input and output, to add two numbers, because we are not explicitly telling the machine to add two numbers, but instead of that, we say, okay, here is the input and here is the output. Just go and figure out how to move from input to output, and give me a program that can do it. Now we can take the program and then load it in the computer and then give a new input and get the output, right? So what is the advantage now? The advantage is that we don't need to sit and explicitly figure out the sequence of steps to solve a problem and then convert that into a program in a manual way. This is all automatic. The disadvantage is that we have to generate a lot of examples, but let's say if we have a lot of examples, then we can do that. That's the key. Okay, so what is the difference? In the human generated, it's sort of, we generated it, so we can look at it, we can analyze it, and we can say, okay, so this is what it is. On the other hand, the computer generated one, we often call that as a model. It's often not, computers will understand, right? So again, the difference is the human generated one, humans can understand, computer can understand. The computer generated one, computers can understand, but humans often cannot understand. So that's the sort of the catch here. Okay, so let's go a little bit deeper into machine learning and say, I'm going to give some examples of different classes of machine learning methodologies and how these methodologies are used in science. Okay, so machine learning, it's very similar to human way of learning. Okay, so, broadly speaking, there are three classes of machine learning methods. The first one is supervised learning, which is very similar to how we learn from our parents, from our teachers, from our mentors. So someone is there to supervise and we learn from them, right? So that's sort of the supervised learning. And unsupervised learning is something that it's pretty similar to how we when we were kids, how we look at the world and learn many things without explicit supervision. We know the world is made up of many objects, and the objects have symmetries, the objects have colors. Of course, someone has to come and say, this is a table and this is a chair, and that's a label that we associate to those objects. But even before that, we learn to recognize those tables and chairs without anyone coming and telling us this is a table and this is a chair. Right? So that's unsupervised learning. Reinforcement learning is something close to how we learn for the trial and error. We try something, it's not working, so I'm going to change my strategy and try to learn something different, and so on and so forth. So that's reinforcement learning. Okay, so let's first look at supervised learning. Okay, this is the question. So what is difficult for a computer? To recognize that this image is a cat, or to send a rocket to the Mars? Okay. The answer is, as we all know, we just landed. We, as a sense, like as humans, we landed the Mars Perseverance recently, and it was fantastic to watch. On the other hand, you take any state-of-the-art cat image recognition system. It's so brittle. I can add a little bit of noise to this cat image, and make the state-of-the-art machine learning system to go bad, or state-of-the-art image recognition system to go bad. Like instead of recognizing this as a cat, it can sort of recognize this as a dog. So that's the problem. So which means, we have figured out the physics and the math of sending rocket to Mars, but not how our brain works in sort of figuring out a cat is a cat, because cat comes in different forms and it has different lighting conditions and so on and so forth, right? So it's quite hard. So again, the system that can do this very well is our brain, right? So our brain is made up of neurons, and the neurons, the neurons are the sort of the basic units, and these basic units, just by the fact that they are connected to each other and in a specific way, and they make connections dynamically over time and so on and so forth, allows us to do incredible things. And it allows us to get some sort, it allows us to get this learning ability that is unmatched for. So obviously, what happened is, okay, so that's the functional unit. That's a system that we know very well that can do this type of cat recognition very well. So how can we take that and convert that into a computer program? So that's where this modeling process started. And you can see, so the functional unit of brain is this neuron, which has dendrites, nucleus, cell body, and axons. Basically, function is it receives signals from the nearby neurons, and then it sort of transmits that information by axon to the other neuron. So that's the neural network in our brain. And basically, what Frank Rosenblatt, so he came up with this model in 1952, saying that, okay, I can build this artificial neuron which just take inputs from my nearer neurons and just send that information to my other neurons. That's it. That's the functional model. And I'm going to convert that into a computer model. Okay. As a result, what we got is neural networks. So the neural networks, how we sort of learn neural networks is that, we give, so you see this is a neural network, and then we have to generate input-output examples. So remember the simple problem of adding two numbers. We give input and output, right? So again, here, set of all inputs. So these are different images, and the output basically saying this is a cat, this is a dog, and horse, and so on and so forth, right? So the very fact that we are giving the output to each of that input makes this problem supervised learning. So we give those examples to the neural network, and this neuron has some sort of weights. The weight determines how much this signal is sort of amplified and so on and so forth. That's it. And then you give that, and then the neural network undergoes a process called training. And once you train with all those images, what you get is sort of a model. Okay, that model, use that model. Now you can give a new image and ask what this is, right? So that's essentially supervised learning. And then the training process here is essentially it's essentially mathematical operations that involves a lot of matrix multiplications and calculus. That's it. So that's why I said this is loosely inspired by neural network, but it is a lot more, it has a lot more math in it as opposed to how the neurons and how our brain works. So it's loosely inspired, but there's a lot of math that goes behind this training to make the system work. Okay, so how we train, or what is happening recently is that it's not just one set of neurons that people use, but they can use a lot of neurons, and they can keep on stacking up the layers. So here, what you see here is 2 layers, but instead of 2 layers, you can stack 100 layers, and that's where these neural networks are getting a lot more power to classify and to identify objects from the images. Okay, once trained, we can go and look at what is happening inside, and I find this is sort of very intriguing. And after training, you can go and look at what is these layers learning. So what you can see here is the edges, which are the layers that are close to the input learns edges. So these type of edges from the images, and then the layer above it learns textures, And then above it learns patterns, and then parts, and then objects. So the more you go up, the complex the objects are becoming. So this is how this neural network is sort of figuring out how to recognize different aspects of the images. So it's basically identifying the edges and taking those edges, put together that as a textures, and then textures are put together as a patterns, and so on and so forth. The beauty of this is the following. This has a pretty close, or it is very similar to how our brain processes the information. And I find that as very, very intriguing, because you have this mechanistic model, you sort of reduced everything to this simple neuron, and you multiply those numbers, and eventually what you get is something close to how the brain processes the information. Okay. So such a kind of system you can already find in your daily lives, in your cell phone, face recognition, speech and language, shopping in Amazon, or watching movies in Netflix, and autonomous driving already finding place. These type of systems already finding place in healthcare and finance. What we are doing at the lab within DOE is making these methods and making this, leveraging these methods to advance scientific discovery. Okay. The first example that I would like to present is this example from the ATLAS experiment. So ATLAS, you all know, it's a detector system that tries to study subatomic particles. It's in CERN. You can look at the scale. So this is the human standing. So this is the size of the accelerator, and this is just one segment, right? And think of the number of, or think of the size of data. So basically, in this detector, what happens is you accelerate particles at near speed of light and make them collide, so that the subatomic particles inside the nucleus of the atom can come out, and you want to detect them. And the scientists have some sort of theory, and the theory is converted into simulation, and they can generate the data. And we can use the simulation data as a training data, right? Recall this cat dog input output example. So we can generate different types of subatomic particles and their names, right, as a sort of input output, and then train a system, and then take that system and then go to this big detector, and then from the experiments we can take the data and then use the system that we trained with the simulation to identify the subatomic particles in the detector. And we want to do that inside the detector. What is the advantage? The advantage is, the training is a slow process, okay? The training takes time, but once trained, you can do inference, that is prediction, in sub-millisecond. So you can throw millions of data points at the system, and you can get this classification in a second, okay? That is a transformational capability. Before, you have to collect the data, you have to process the data, and then the scientists have to go through this data and figure out how to do this. They have sort of system, that rule-based system that tries to identify these particles, which are never robust. And now we can do all this at the edge near the detector by collecting the data, and then immediately get those type of detections. And thanks to supervised learning, we can do this at a very short period of time. So this is another example. This is another example of accelerating cosmology research. So what you see here is something called gravitational lensing. We all know light travels in a straight line, right? But in the figure, in the video, what you are seeing is the light travels in the straight line, but a heavy object in the path, right, in the space, can bend the space-time curve, right? The space-time continuum. And because of that, the light is going to bend. That's a fantastic phenomenon. Einstein predicted it way before. And now the point is, we can look at the sky, we can collect thousands and thousands of images and trying to analyze those images. And again, the amount of data that we are collecting is quite large, and we cannot afford to do this processing even in a semi-automatic way. So one of the things that we are trying to do is, to make this end-to-end pipeline, end-to-end analysis, take the image and then find the lensed image. So that's the sort of, it has a series of steps. And what you see here is this. So this is how the image look like, the gravitational lensed image look like. So you see with the noise and everything. So that's the resolution that we get. And then from that, first we have to denoise it and then deblend it. And then finally we can extract the lens. See the input image and how the lensed image looks like. And before, each of this stage is sort of, manually curated and manually processed and so on and so forth. Now, using supervised learning, we give this image and then we can get this image. How we do that? Again, we have theories and we have the models about all about the gravitational lenses, right? And we can do simulation. And using the simulation, we have models for the noise, we have the model for the blending and so on and so forth. Again, we can generate lots of these images artificially using those models, using those simulations, train a machine learning model, and then use that model to go and do this end-to-end conversion from the real image. Okay, and then we can do that, as I said before, millions of images in a second, right? So that's the transformational capability, and we can analyze a lot more data. And the telescopes are going to get bigger and bigger, and the amount of data that we are going to collect is also going to increase. So these type of capabilities, it's not a sort of a luxury anymore, but it is imperative. It is essential to analyze large amount of data. In another project, we are looking at traffic congestion. Okay, so you don't deal with cosmology probably or the CERN experiments, but I bet you might have stayed in a traffic for a while in your life, or at least several times. So Department of Energy is interested in addressing this problem, for various reasons. One is productivity, the other is emissions and how to make the infrastructure a lot more efficient and so on and so forth. So the previously, you can take this, you can look at this problem more from a physics perspective, trying to model the traffic, how it evolves, and so on and so forth. And now what we are doing is we have a lot of sensors on the road, and we can collect the data. And now we can use the data and train a machine learning model and use the model to forecast the traffic. And more importantly, we can use such model to identify traffic congestions and the ripple effect due to accidents. And ability to do that 30 minutes in advance means the traffic management centers can reroute the traffic in a much better way. So just ability to predict what will happen 30 minutes in advance, we can reroute traffic in a much better way to avoid congestions related to incidents and so on and so forth. And we are doing that with supervised learning. This is another fun project that we did for City of Chicago. City of Chicago has several health inspections that they have to do, and one of that is restaurant inspections. So they have to send inspectors in a round-robin way to different restaurants to find out whether they are violating the health norms and things like that. So typical way they do it is random checking, right? So that's what they were doing. And the point is now they have 10 years of data from the inspection, and we have built sort of okay, so we sort of correlated multiple sources of data like weather, 311 calls, the rat issues, and so on and so forth. We have that sort of database. We correlated that. We took that data and the inspection data and then trained a supervised learning model and use that. So on a given day, can we identify 10 restaurants where we can, which has high probability of violating the health norms, so that we can send the health inspectors to those restaurants as opposed to the previous strategy of just sending them randomly. And then we did this sort of pilot study where we found that AI methods can predict violations at least 7 days in advance. Again, it's a pretty cool application. Okay, so with that, I want to go to the second methodology, which is challenging methodology, but it has a lot of applications. So imagine the supervised learning has this problem of labeling, right? So one has to give the input and output examples, but unsupervised is a lot more sort of, you don't need output, right? So which means that you don't need human in the loop. Can we do something without humans or without labels? These methodologies are sort of centered around that idea, unsupervised learning. Okay, so often I ask this question, so how many of these phases are not real? How many of these phases are computer generated? And often, can take a moment and look at it. And the answer is all these images are computer generated. So none of them exist in real world. Okay, so these are all generated by neural networks. And you can see this link, this person doesn't exist. If you go to this website, you can go and sort of, refresh this page each time the computer generates one new phase, and that phase doesn't exist in the world. Okay, how to do that, right? So these are several implications. First and foremost, let's say, so the way that we try, they train the system is, takes set of all images, right? Set of all human images and train a neural network. And once the neural network is trained, you can ask the neural network to generate new images. And as a result, you see there is only input, there is no output. And you see there is no prediction, but you just from the model, you can query and then generate more examples. So what is the implication of it? So we didn't explicitly say how a human face look like. Okay, the human face has 2 eyes, 1 nose, 1 mouth, and so on and so forth. Instead of that, we just generate a lot of input examples, right? Because that is, in many fields, that is easy to do. And then we let the system to learn the features of those images. And once they learn these features, we can query this model to generate artificial images that satisfy those features, that satisfy so the different correlations that were learned from those images. Okay, that is fascinating. The reason is the following: we use those type of methodologies to generate new chemicals and materials and molecules. Okay, how? We can take a set of all molecules, set of all known molecules, and that's a lot. We doesn't know about their properties. Let's say, but we can generate lots and lots of molecules, right? Takes as an input and train a neural network. And once we train the neural network, then we can go and query the neural network to generate synthetic molecules. The synthetic molecules that doesn't exist today, but that are sort of similar to what we have in the real world, but they might have interesting properties. You can use this kind of techniques, for example, for new drug discovery, where you say you take the molecules, the small molecules which are used as drugs, and then train a neural network, and then now you can go and query from that model to generate candidates, synthetic candidates, and then you can use those synthetic candidates for post-analysis and so on and so forth to figure out, okay, here are the 4 promising synthetic candidates. Can I go and do this in the lab, or can I run that? Can I run a molecular dynamics simulation for those synthetic candidates and see what their properties are, and so on and so forth. And this is a transformational technology because ability to generate synthetic molecules without explicitly programming what a molecule look like and how the bonds look like, and et cetera, that is great. Okay, so I'm at this final thing on reinforcement learning, which is like learning by trial and error. So what this approach is primarily, let's say you have an agent and it performs an action in an environment and it gets a reward. And using that reward, it performs the next set of actions. Okay, simple framework, but it's a very powerful approach for many problems. So to illustrate the efficiency of reinforcement learning, let's consider this game. Everyone might have played this game at some point of their early childhood. Like, it's a paddle game. You have to send the ball to the other side, and if someone misses, then you score, right? Okay. So if you have to design a supervised learning system, if you want to design a computer that can play this game, how can we do this? Well, let's say, someone is playing and we observe like, okay, so this is the image. And after seeing this image, someone is pressing down. And if this is the image, someone is pressing down. And this is an image and someone is pressing up, and so on and so forth, right? So you can collect lots of these examples and train a supervised learning system. And then you get a model. And then when you want to, and then you deploy it for playing, right? So when you play, then there is this new image. So you see the frame, and then you decide whether to move up or down, and the model will tell you whether to move up or down. So what is the disadvantage of this approach, the supervised learning approach? First of all, you need large amount of training data, right? Supervised learning suffers from this problem of large training data. And the second thing is, let's say, you hired me, who's like sort of a mediocre player in this game, and collected training examples. And the system that you are going to build is going to be as good as the training examples, right? As good as me. But in many settings, that's not what you want. You want to build a system that sort of outperforms human performance or outperforms the baseline performance. In those cases, supervised learning is not a good idea, right? So that's where reinforcement learning comes in. And reinforcement learning, again, if you look at this, so basically you will put a neural network, right? The frames will go into a neural network, and the neural network will decide to move up or down, right? So that's a simple approach. And based on this score, the scores are given as a reward to this agent. And basically what happens is the neural network in the beginning, it will make random moves, random up or down, it will lose, and sometimes it will win. And as soon as it starts figuring out how to win, that will be sort of reinforced. So it will start making moves that eventually results in good scores, and it will try to avoid moves that eventually resulted in the score for the opponent. And the advantage is that it will be slow. It is going to be slow, but then the point is there is no human involved. You can just write this code and let them train forever, right? Let go for 1 week without any issues, right? Once you train that, then the resulting system is going to be a lot more powerful as opposed to the supervised learning example where a human is involved, right? Such an approach, so this is sort of a milestone, a milestone phase in reinforcement learning. It's old, but I still want to point out that, like, such a reinforcement learning system has resulted in building powerful automated game system where, this one, the game of Go, it's much more complicated than chess, right? Before reinforcement learning, the computers were sort of average players. When the computer plays this game, an average player can easily beat a computer. But then after reinforcement learning came into picture, when Google built this reinforcement learning system, it went on to beat the world champion 4-1. So the world champion is like 18 times world champion, and it sort of beat the world champion 4-1. And after that, there are several new cool work that came from Google on building or advancing the reinforcement learning, and probably some of them you have already saw in the public press. But this is a sort of the milestone moment where, say, reinforcement learning came. Before that, it was more like an academic exercise, but this is the phase where it's it can really outperform humans in really complicated tasks. Okay, so what we are doing using reinforcement learning. So take for example, so we are using reinforcement learning to automate AI development. So what does it mean? So take for example this cancer drug discovery neural network, where you say, okay, you have medicines and you have the tumor, and you have a lot of data on that, and we want to build a neural network that says, given a drug and a tumor, is it a good or bad? Like, this drug is good for this tumor or not, right? So that's the thing that we want to learn. And developing a neural network for this problem is very, very hard, because the neural network, you can think of this as sort of a, Lego blocks. You have to try out many different components to figure out what is the right one. If there is something like, an image or text analysis, Google have already built models and you can go and use them. But on the other hand, if you are looking at, this type of science problems that have, no one has looked at, then you have to face this problem. Okay, what is the right type of neural network that can do the job for me? And for example, a simple neural network can have, millions and millions of possible designs, or you can build, try different possible combinations, millions of different possible combinations. And often the humans become the bottleneck there. So they have to figure out what is the right design and so on and so forth. So what we did is to use reinforcement learning to automatically construct this neural network, which means that the reinforcement learning method will basically try out different possibilities. And from the accuracy value that it is getting, it will learn how to build better neural networks. And this is what we found out. So what you see in this plot, in this plot, like higher the better. One is on the accuracy, the other one is on the inference speed. But what you see here, the yellow is the human generated one, which took several weeks. Okay, the red ones are reinforcement learning generated ones. So it's basically the reinforcement learning figured out how to build better models than humans in just 6 hours, right? In 6 hours, not one model, but we generated hundreds of different models that outperformed the human expert developed model. Okay, so that means, so that is a transformational capability for drug discovery, right? So now we can automate this process, and that is a new capability. Okay, so moving forward, there are many aspects, and we are just scratching the surface what artificial intelligence and machine learning can do for science. And if intelligence is a cake, okay, so supervised learning, which is like, it's prevalent everywhere, and it's sort of, it's a highly data driven, and it's sort of the icing of the cake, right? So it's just the outside. But the real cake is actually unsupervised and reinforcement learning, at least for the science, because in many science domains, we don't have a lot of data because the simulations are expensive, and generating the data is a bottleneck, and so on and so forth, as opposed to Google's and Facebook's, where users upload the data and they have access to a lot of data. But science domain is, many science domains, we don't have a lot of data. In those cases, we have unsupervised and reinforcement learning as the methods of choice. So I'm almost at the end, but I wanted to point out this study and what reinforcement learning means for science. So this is again another example where this is a game. Probably you already know this game, and they let a human to learn this game and play, and the reinforcement learning agent to learn this game and play. So what you see here, the original one, right? This original game is one in which humans bring a lot of knowledge into this game, because they know based on the shape, they say it's a danger and they can jump away and so on and so forth. So they don't, they bring a lot of this real world knowledge into the game, and eventually they can outperform reinforcement learning here in terms of learning efficiency. So that is expected. But this is what happened after that. They started changing the game. Okay, for example, they masked the semantics. Instead of showing the danger, they masked it and they reversed the semantics. For example, the gold one is actually a danger, and this one, the pink one, is actually is not a danger. So basically, they reverse the semantics and so on and so forth. And then they went on to do something like changing the gravity. So instead of moving up and down, they moved sideways. The gravity acts in sideways. Okay, what happened is this. As the complexity of the game increased with respect to the semantics, the reinforcement learning agent became more and more efficient. In other words, the reinforcement learning took the same time to learn this original game, whereas the humans were completely outperformed in this setting where your semantics are completely different. And that is fantastic for science because often we are in that regime. So we are often in the regime of unknown when we are talking about far equilibrium phenomena or computational fluid dynamics, where we cannot resolve the underlying physics and so on and so forth. Our prior knowledge often is limited, and we cannot just develop first principle models to keep advancing those areas. And having reinforcement learning is great because it will try different possibilities and figure out what is the right thing to do, as opposed to humans in the loop and trying to figure out what is really happening. So in this way, AI methods have, this type of reinforcement learning methods are great for generating new hypotheses and experiments and many more. We are also working on insect brain-like hardware and algorithms for AI edge. So far, I talked about AI as sort of something at the large computing facilities and so on and related technologies, but don't underestimate the intelligence of this Drosophila brain. This is the fruit fly brain. It's the order of 10,000 neurons, but it can do remarkable things. And those type of intelligence are great for edge type devices, where, let's say, we are installing sensors in the city of Chicago, where we want to do learning and prediction at the edge. We don't want to take the data and move to a computing facility where we can do all this cool stuff, but we want to do it at the edge. And these type of insect brain-like hardware and software are a lot more appropriate for this. So it's called AI at the edge. And this is also highly relevant for our light source facilities, right? So because it generates a lot of data, we cannot afford to move all the data to the supercomputing facility to analyze them. Instead of that, as soon as the data is generated, can we find ways to reduce the data? Can we find ways to sort of analyze the data at the edge and figure out what is the right data and what is the good data, and transmit only good data to the computing facilities? So we're also working on custom chips, custom algorithms that are sort of inspired by insects. Okay, so so the requirements are many, right? So one is like on the edge side, we have a lot of data at the experimental facilities, and we are also pretty excited by exascale computing. So Argonne is going to get one of the first exascale supercomputer, which can perform 10 to the power of 18 operations per second. And that's the picture that you see here, Aurora. And this machine is custom built for running simulation and AI and machine learning at the same time. And a lot of new engineering went into this machine, and we are pretty excited to sort of make simulations 1,000 times faster or 1,000,000 times faster. For example, weather simulations are very, very time consuming, and with this type of machines and artificial intelligence, we can sort of reduce the time for weather simulations by 2 orders or even 3 orders of magnitude. And that will allow us to do ensemble simulations. Like instead of running 10 model ensembles, we can run 1,000,000 model ensembles and get really good weather predictions. Okay, so I'm at the end, and I want to say I can't wait to see many things what AI can potentially do and how AI can potentially transform science in the national labs, not only in the national labs, throughout the scientific discipline. I can't wait to see how AI and supercomputer will be used for mapping and understanding human brains. So this is a cool project by Bobby Kasturi from University of Chicago and Argonne. And I can't wait to see how AI and supercomputers will be used, or will enable new drug discovery for cancer. In fact, those technologies, we sort of transformed that for COVID recently, and it was pretty fascinating what Rick Stevens' team has achieved in this space. Can't wait to see how AI is going to unlock the mysteries of the universe It's a very cool project, again, from Argonne's Salman Habib and his team. And we are using AI for finding new battery materials, and can't wait to see how AI can accelerate this material discovery and so on and so forth. So I'm cautiously optimistic, but I'm also pretty excited. And I can't wait to see AI-enabled technology helping scientists to win Nobel Prize, and I expect that to happen very, very soon. Acknowledgements, Department of Energy, DOE Early Career Research Program, and several offices within DOE. I'm very grateful to the support from these offices. And thank you for your time and for attending this talk. And I have the link for internship opportunities at the national labs. I'm happy to share that after the talk, or please reach out to me or to Jasmine. She has all the resources. She will be able to provide you with this information as well. And finally, I open for questions. Thank you.
Thank you, Prasanna, for the excellent talk. So now we have a little over half an hour for questions. Unfortunately, I have to go shortly, so I'll leave the moderation to Professor Castillo. And if anyone has questions for Prasanna, feel free to ask them.
Thank you, Professor Paulo.
Okay, everybody, the floor is open.
Does Argonne have any projects applying AI to better AI design?
Which design? Battery?
Better AI design.
Better AI design. You mean to make AI better?
Exactly.
Yes. So so we are doing that in multiple fronts. So the one is the automated machine learning that I talked about. This is about machine learning development or AI development is still human centric. It's a human expert centric, which means that the experts develop these methods, and we are looking to automate that using supercomputers. So that's one thing. The other thing is to improve the robustness and the fairness of these methods. So I didn't go really deep into that, but the two things that I wanted to touch upon is the robustness of these methods, right? So let's say this is not about you deploy this and say, okay, I'm classifying cat as a dog, which is acceptable in the real world. But on the other hand, if you're looking into drug discovery, if you tag a bad drug as a good drug, then you bring the whole scientific rigor into question. So how to make these methods a lot more robust and how to make these methods effective to these type of false positives and things like that. So these are the other sort of research area that we focus on, and finally, looking at uncertainty quantification, which is not a big topic in the industry, but in science, it's very, very crucial, because at the end of the day, we are doing approximation, and if you don't have uncertainties from these models, scientists will not believe us. We cannot just ship a model to a material scientist asking him to believe this model, trust this model. So we are developing trust and uncertainty quantification methods to quantify the robustness of these models.
Hey, can you get your adder and or subtractor to add irrational numbers?
It is possible, provided if you can generate a lot of examples. It's not going to be as straightforward, but there are recent neural network developments that can work with complex numbers and the irrational numbers as well. So yes, the answer is yes. but it's not going to be as straightforward as the addition of two numbers as subtraction.
Excuse me, Dr. Balaprakash. I have a question regarding what you had brought up about these model uncertainties. So when using machine learning or AI, any sort of AI to create a model, right? The models from my background are just some sort of clever interpolations mainly, right? So the functions that are created from these models, is there any work at the labs being done to understand what the models physically represent, if they are meant to have some sort of, that they're applied to a physical discipline like in the earth sciences? Because what's the point of coming up with a model from these AIs if there's little meaning that can be determined from them? Yeah.
So we call that as explainable and interpretable AI. I totally agree with you. So, one thing, there is a thing to build a interpolator, but what can we learn from that interpolator? That is often critical for the scientists. So it is domain specific, so to speak, right? So, for example, the material science and the moleculars and the cancer drug discovery and so on and so forth, we use a lot of graph neural networks, and we use we use related explanation, explainable AI methods to sort of identify which bonds and which sort of segments in the molecule contribute to this particular property, and so on and so forth. So that's so that's for, let's say, if you are using graph neural network. And for a fully connected neural network, for let's say we are using that for some other problems. We use a combination of methods, using something related to the instance wise. So you can basically take the examples and you perturbate and then see what the model is doing. And those type of perturbations will allow us to see what is the model robustness, and can we learn something from that. And there are other explainable and explainable AI methods, such as I forgot immediately, but the game theoretic approaches and so on and so forth, is basically take the trained model and you can look at the impact of each inputs on the output and so on and so forth. So that we find this in several of these examples, several of the use cases are quite informative. So yeah, there are. So the answer is, there's not a single approach. There are a class of approach, and often this is related to a particular model and particular domain.
Thank you very much. I'll let anyone else go if they have a question.
Other questions? Okay.
I have a question. I don't know if this is something you can speak to, but we kind of had this conversation, a few of us students last week. Specifically, a lot of us are computational science students. And so at the national labs, are you looking more for people who are specialized in a very specific domain, or in the world of computer science or computational science? Are you looking for more jack of all trades who can be applied to multi problems?
We are looking for both. So, I work with computational science people, in a particular, let's say, computational fluid dynamics people in fusion science. So they are, they do modeling, and their career is very their research expertise is very focused on, let's say, for the fusion science, plasmas and related things. On the other hand, so those are my collaborators, but I have colleagues in my division, mathematics and computer science division, who are CFD generalists who can adapt to different applications. Okay, at the end of the day, these are CFD, whether it's a weather or plasma fusion science, our engine simulation, and so on and so forth. At the end of the day, we do have software such as NEC5K and so on and so forth. This is basically computational fluid dynamics at scale, and those are sort of generalists. They will serve different applications, but they more on the side of innovative methodologies for computational science and computational fluid dynamics. So national labs need both type of people, experts in one particular area and generalists who can innovate the methodologies and bring those methodologies to a specific domain.
Thank you.
Any other question? Okay, in that case, I want to thank our speaker one more time for a very informative and well delivered presentation. And thank you everybody for attending, and have a wonderful weekend.